Okay, welcome everyone. Just a quick video to help out anyone with the LTSpice simulation of the common emitter amplifier lab. So here I have the lab set up. It is the same circuit from the lab manual. Now, a couple of things. Let's talk about the signal that you're applying to the input of this amplifier. It's this sine wave over here. Sorry, I had my pointer on the wrong screen. So we're just using a regular voltage source. We set it up to be a sine wave. We have 0 for the DC offset. We're going to have this centered at 0 volts. And then the amplitude is going to be 0.5 volts. So half a volt, and that should be the peak voltage is what LTSpice has you enter for that. And then the frequency would be 1 kilohertz, so I just put 1K in there. That's all you have to set up for this, and hit OK. I have my ground set up for everything, and now let's talk about the simulation time. So if you go to simulate and edit simulation time, I have mine set up at 0.006, and the reason I have it set up at 6 milliseconds is because our input signal is a 1000 hertz or 1K hertz frequency, 1 kilohertz. So I do 1 divided by the frequency gets me the period, so that's 1 cycle. I want to show 6 cycles on the screen, so I will multiply this number by 6 so that the simulation time runs for exactly the same time as 6 cycles of our input signal. So that's where the 0.006 or 6 milliseconds comes from. So I'll close that, and I will close this. It's all we need. We're just going to do a transient analysis on this. Hit OK. And I do have a 15-volt source here tied up to the top of this voltage divider bias, as well as the collector circuit of my amplifier. Ground down here, I have all of my caps and resistors in place. Let's talk about the NPN transistor that we're doing here. So if I go ahead and delete this, if I hit F2 to bring up my components and I just select NPN transistor over here, hit OK, place that down. And if I right click on it, I can pick new transistor. Since for this lab, we're going to be doing the 2N3904 NPN transistor, that's a general purpose BJT. I'll go ahead and sort according to part, and I will look for 2N3904. And I'll just grab the first one over here by the manufacturer, Philips. Many different companies make this transistor. It's been around with us for quite a while, and it's just kind of the stereotypical NPN transistor that everyone always uses. They're a dime a dozen. Okay, let's hit OK. We set that up. Okay, so now we have a transistor here. We have our 15 volts, our voltage divider, our decoupling cap here. Keep in mind this resistor that's here is actually considered to be part of the source. This is the output impedance of our source. And similarly, our load is over here that we are driving our 10K load over here. Aside from that, everything is set up, so I should be able to just run this and take a look at the input versus the output. So let's go ahead, let's run the simulation, and let's first take a look at this voltage. This is the ideal voltage. This is what our source is producing. And it's 500 millivolts peak, and it's centered around 0. It's at a 1 kilohertz frequency. And yeah, it looks nice. Now, if I measure between this resistor, and keep in mind, this resistor is the output impedance of the source. Every source, everything that you ever connect up to a circuit, whether explicitly stated or not, has some output impedance. And so if I measure right here between the C1 cap and the output impedance of my source, I will be measuring the effect of my output impedance of the source and the input impedance of my amplifier. So just as we showed, and in fact, let me just go ahead and draw this. Why not? Let me just grab a piece of paper here. And let me turn on my whiteboard. So the circuit that we just saw can absolutely be modeled, and you are doing that using that generic amplifier. So when you're calculating that amplifier parameter, you're calculating it for the whole common emitter. And this generic amplifier model is just a substitute. It's a stand-in for our circuit. And it's actually a stand-in for everything, including that capacitor all the way to the voltage divider bias, including the transistor, including all of that circuitry. So the RS is that 50 ohm R1 that I have in my circuit. So if I switch back over here, this is RS right here. And as I said, it's a fact of life. We just have to live with that. And then Zin would be whatever you calculated for your amplifier parameters. So here's the point. We know that our Vin has a plus and a minus here. We know that the voltage at this point with respect to ground over here is a combination of whatever our source is times Zin divided by RS plus Zin. Again, that's the voltage divider equation. So when I measure on my schematic between R1 and C1, I am measuring Vin. I'm measuring this voltage here, and I expect that it should be less than the voltage source. Not by much, but by a little. So if I go back over to LTSpice over here, and if I measure between here, I should get a slightly, very slightly smaller voltage than my source, because the measurement at this point takes into account the output impedance of the source, R1, that 50 ohms, as well as the input impedance of the amplifier. So, okay, they actually look like they're the same. Let me zoom in over here and kind of show you that difference. They're very close to each other. Okay, so if I go ahead and put this anywhere, let's go ahead and also bring up the second cursor for our V1, and I'm going to put that right there next to it. Okay, it's a subtle difference, but that difference is there. It is 0.2567 versus 0.2564. Okay, it's not much of a difference, but that is because we are correctly paying attention to our impedances in this example. If I go back to the whiteboard over here, I have a low impedance and I have a high impedance on my amplifier. And remember, this is just a stand-in for our entire circuit. This is pretty low. 50 ohms is fairly low, and Zin is actually pretty high. So we're not going to see much of a difference, but let me show you what happens if I go ahead and increase this RS value. Let's say we don't have an ideal source. Let's say we have a source that's displaying an output impedance of, you know, something closer 200, 300 ohms, 500 ohms, something like that. Let's go ahead and see what that difference ends up turning into. So I'm going to jump back over to over here. Let's close this and let's zoom out to its full extent. And let me change 50 ohms. Let's make this 500 ohms. Okay. Now if I simulate, notice that gap just got a bit larger. Okay. So over here, you can now see the difference. And if I take a measurement, let's go between the peak there and, oh, now I got them on, there we go. Different. I'll put them side by side over here. Okay, so now 0.247 versus 0.249. Okay, so a little bit bigger of a difference in that case. Still negligible in my opinion, and that's just because we have a fairly high impedance on the input to this common emitter amplifier. Okay, of course, as I increase my impedance on the output of the source, so if I make this something more like 10K, now you're going to start to see a very drastic difference. Yeah, that's huge. Now, this is the type of thing that inadvertently people will connect up to like an embedded system to the input pin of a microcontroller, and then they'll wonder why their values are off by like, you know, 0.2 volts or something like that. So we do have to be mindful of our impedances. However, the lab that I set up on the input does not suffer from a problem from this impedance issue. So let me go ahead, turn this back to our 50 ohm output impedance. Simulate, run. Okay, we're good there. Okay, so for all practical purposes, these are the same because we're driving a high impedance input with a low impedance output. Golden rule of signals, always, always drive a high impedance input with a low impedance output. Okay, let's go ahead and now let's just look at the input here. So this is the input Vin, taking into account that impedance, those impedances, which is an ideal setup right now. Now let's go ahead and look at the output. Okay, the output is in green. Now the output, if you notice, has, well, first off, look, the two are inverted as they are supposed to be. A common emitter amplifier does invert the signal, as I've spoken about a couple of times in class, and that's just the relationship between the voltage driving the base up and down versus where we're taking our signal. We're taking our signal from the top of this BJT over here. So as current goes through here and as it increases, the voltage goes up as it's applied here. The current through here increases, the voltage goes up across VCE, and as the voltage across VCE gets larger, this gets smaller. So you get an inversely proportional relationship. Okay. And could just go back to any of the lecture videos for the clarification on that. I think I hit this point about 2 lectures ago or 3 lectures ago. I spent about 10 minutes explaining that. Okay, so, okay, inverted, 180 degrees out of phase. Now, there is a little extra of a phase shift over here. If you notice, the peaks and the troughs do not line up perfectly. That's okay. I'm not, one thing I am not covering in this class very much is the phase shift that you get with an amplifier. Every amplifier is going to give you some amount of phase shift. Every filter, everything that affects your signal, you just have propagation delay in there. So we have a little bit of phase shift. That's okay, but generally speaking, we are 180 degrees out of phase, or you can consider our output to be inverted relative to our input. Now let's talk about magnitude. After all, common emitter amplifier, it's in the name, amplifier. That's what we care about. We care about taking small signals, making them larger. Many times, almost every time that you hook up a sensor to a microcontroller, anytime you hook up something to an FPGA, generally speaking, if you're measuring the outside world, if you're measuring the world we live in with a temperature sensor or a ranging sensor for distance or any type of phototransistor for measuring light intensity. You know, these are things commonly that are done with embedded systems, because the whole point is to interact with the actual world, as opposed to just running desktop applications on some general purpose computing machine. So, you know, signal amplification is important to us. We should definitely know how to do this. After all, that's what makes us not a hobbyist in this realm. So let's double check. Let's see what the amplification ended up being. So now that I'm looking at my output, I'm going to set up one cursor at the peak of my actually my input signal, and let's go ahead and click on the green one a second time. Switch back. There we go. All right, so let's measure the top of the blue and the top of the green. Okay, so now I'm looking at the peak of the input versus the peak in the output. And over here you can see that my input, see if I can get this a little closer to, yeah, 4.498 millivolts. So not quite exactly 500 millivolts. That's a function of that impedance. The output is 2.275. Okay, so if we go ahead and divide those numbers, we can find out the real gain of this amplifier. So gain is always, let me pull up my whiteboard. Gain of any amplifier, gain of anything, any system, is always defined as V out divided by V in. We used this in our AC analysis of the amplifier when we wanted to derive the gain. And actually, I should say gain. I should say AV for voltage gain. A is used for gain, V is for voltage gain. The voltage gain is always defined as V out divided by V in. So if I go ahead and now I have my measurements from LTSpice and I divide those two, V out by V in, I should get my gain of this amplifier. Don't get confused. This is different than the gain that you calculated for the generic amplifier buffer. Okay, because this gain that we're calculating is includes all impedances of our source, our amplifier input impedance, our output impedance of the amplifier, as well as the input impedance of our load. So don't get those confused. The AC parameters that you calculated by hand in order to derive that generic amplifier model, that gain, in the lecture, I referred to it as open loop gain. In other words, not connected to anything. So let's go ahead and let's do that calculation over here. Let me drop my whiteboard and let's do, I have cursor 2 is the one that's looking at the output. So let's do 2.275. Come on, 2.275 divided by 498. Divided by 0.498. Okay, that gives us our actual amplification. It's 4.57. I'll do 4.568. Okay, so that's what I got there. Okay, now keep in mind with our common emitter amplifier, our output impedance is really not that low. It's kind of considered to be a medium output impedance. And so this is why in the lab I'm asking to check this with two different loads. One that is a high impedance and another one that is a low impedance. And so the, the output, if I change this to 1K, it will have a lower impedance. And then I'm going to be in that situation where I'm trying to drive a low impedance with a medium impedance. So I get the feeling my output signal is going to get squashed a little bit here. That's my technical word for it, squashed. Mismatching the impedances causes signals to get squashed or smashed. So let me go ahead, change this 10K over to 1K. And just to keep in mind, let's grab that number before I run this. 2.273. Okay, I'm going to remember that number. Let's go ahead and now let's run it with that lower impedance load. Simulation run. Yeah, that's what I expected. Okay, so look at what that value just went to. It went to 702 millivolts. That's huge. That's huge. Okay. Yeah, it's just a feature of a common emitter amplifier. And that's why I showed another type of amplifier that can address that problem. And then you could go ahead and cascade them if you wanted to solve that problem and be able to drive lower impedance things. Okay, so let me go back to my whiteboard here and kind of... Okay, so this was with a load. Let me switch to blue. Okay, this is because our load, when we had a 10K, we had an output that, well, it was correct. And once we changed that load to 1K, all of a sudden we needed a lot more current to drive a 1K load because, well, it's Ohm's law. And so the more current it takes, the less ability our amplifier has of supplying that current. And so we see that manifest itself as a drop in this voltage. We should have gotten 2.273, but we didn't. We got 7.02 millivolts. And so when you calculated the gain for this amplifier, you got a number that was much closer to this. Whereas if we were to now again calculate the voltage gain of our amplifier under the conditions of driving a 1K load, then AV would be equal to, well, V out divided by V in. That's 702 millivolts divided by 497, something like that. 497 millivolts. It was very close to 500 millivolts. And so when you go ahead and calculate the gain now, you're going to see 702 divided by 497 gives us, yeah, a gain of 1.412. Okay. So what I'm doing is I'm illustrating how we are really at the mercy of our impedances at the end of the day. So it doesn't matter how accurate of an amplifier you design. If it isn't low impedance compared to the load that you're trying to drive, you're going to always end up losing your signal. And, you know, this usually in the workplace manifests itself as me just not thinking very much, connecting two things, expecting it to work, and then not asking that very fundamental question of what's the impedance of that thing that I'm connecting to, and what's the impedance of the thing that I'm connecting to the thing. Okay, so anytime you attach two wires together, I don't care where those two wires are, even in this circuit, even here, any two things that you attach to each other has an impedance. It's just sometimes we don't have to pay attention to it, and sometimes we do. In the case of the source driving the input to the amplifier, have to pay attention to it. In the case of the output of the amplifier, driving something, we have to. In the case of connecting a signal to a microcontroller, we have to. In the case of taking an analog measurement, going into some analog digital converter, which you may or may not be familiar with, you absolutely have to pay attention to it. So unfortunately, that's one of those things you're just going to have to see over time, and then see the applicability of this concept. But I promise you, it's very real, and I promise you, it's one of those things that gets us into trouble a lot of times. Okay, so that should help you to develop your LTSpice model, be able to run it, know where to measure and where to look at things. You're going to be measuring the in between the cap C1 and R1, and you're going to be measuring the applied voltage to the load between C3 and the 1K, so right in between here. Okay. Aside from that, it's just some caps and resistors, and you should be able to calculate this all by hand. All right. So hopefully that helps out. Hopefully that explains a bit, and I will catch you guys next time.